This is problem 44 from chapter 6. Chapter 6 is all about conservation of energy and work done by non-conservable forces and all that. But we have a car that's going to be going around a circle. So odds are, if we've got a radius here, r, and I've relabeled it here this way, that'll make sense why I did that in a minute. We're probably also going to some forces along the radius. So as soon as I see a circle where they define r, like they do here in the book, I'm thinking circular motion in addition to conservation of energy. So let's start with that, okay? And we're trying to find the radius r, that's what we're looking for. And the car is to remain in contact with the track at all times, and we're trying to get the largest value. So r is as big as possible. Well, if it's r is as big as possible, meaning the circle or the loop-de-loop here is as tall as possible, we're going to be at the point right where we're about to lose contact, because we want to be going around fast enough to just make it around the circle, which means we're about to fall. Okay, so when I draw my free body diagram, I'm just going to have force of the weight, and that's it. There is some very, very, very small normal force, but it's small enough that I'm going to assume, I'm going to write my assumption here, that the normal force is 0, because we're trying to maximize this r. Let's sum forces now along the radius. And I always like to call the direction towards the center of the circle positive for this summation step. So I'm going to call down positive. And that equals mass times centrifugal acceleration, which is v squared over r. And this is good because we're trying to find r. We've got to get r in our equation or into our formulas somehow. And this is the first place it's popping up. And we just have one force, which is the weight. So mg of the car equals mv squared over r. The mass of the car cancels, which is good because we're not given any information about the mass. But now we're stuck because this velocity, okay, is where I drew this free body diagram for, which is at the highest point. So I'm going to put some numbers on here. I'm going to put a 1 here at the highest point in the loop-de-loop. I'm going to put a 2. So make this v2. Make this v2. And now you can clearly see that we're stuck because we don't know v2. So we can't solve for r. So let's apply something else. And the something else will be conservation of mechanical energy. In this problem, there was no mu given. I'm going to assume that friction is negligible. And as a result of that, I can say work done by non-conserved forces equals 0, which means our ME will stay the same. Remember, this equals delta ME. So 0 change in mechanical energy, ME stays the same. Using my same notation over here with the 1 and the 2, I'll write ME at 1 equals ME at 2. And if I'm going to do an ME stuff, I've got to define where the height is 0. So the lowest point in the problem that I care about, there's my height equals 0. So at point 1, I have a height of 0, so I only have kinetic energy. So that'll be KE1 equals. At point 2, I better be moving, because if I'm not moving, and this is my free body diagram, I'm going to fall down, right? Because I better be moving a little bit so I can keep going along the track. So I am moving, and I have a height. How much is that height? Well, it's the distance from here to here, which, if you look at the circle, this is a radius, or 2r, okay, a height of 2r. And we are moving, so we'll have KE at 2 plus PE at 2. Fill this out, 1/2 mv1 squared plus 1/2 mv2 squared plus mg times for my height. I'm going to go ahead and put in 2r right now since I already figured that out. The m's will cancel. And now here we know v1. We don't know v2, but we have another equation for v2. So at this point, I believe we're at 2 equations, 2 unknowns. I'm going to clean it up a little bit. I'm going to solve this for v2 squared and then plug in over here. Y squared, because I've got another square, just makes my life a little bit easier. So v2 squared equals gr. Now let's substitute. I'm going to take this. I just solved this for v2. I'm going to plug it back in over here. So we have 1/2 v1 squared equals 1/2 the v2 squared becomes gr plus g times 2r. And sure enough, now we've got enough to solve, okay? Because v1 was given. The v1 was 4 meters per second. So 1/2 times 4 meters per second squared equals, we can do this. So we have a 2gr. They have the same g and an r, right? We have the same thing. So it's like 2x plus 1/2 an x. So we'll go ahead and we'll leave it 2.5. Or don't want to leave it like that. Yeah, let's leave it like that. We can just calculate. So 2.5 GR. Oh, and G is 10 or 9.8. We'll go ahead and put in the 9.8. And now we can solve for R. Let me grab the calculator. I think if I'd used 10, we could have done this in our heads, but let's use the 9.8 and get what the book got. So we'll have 16, which is 4 squared, cut in half, that's 8. So 8 divided by 9.8, and then divided by 2.5, and I'm getting 0.327 meters. And let's see what the key got. A little closer here, 0.327 meters. So it worked out. As a quick recap here, that is it. But as a quick recap here, I knew I was going to, or I suspected I was going to have to do something with summing force along the radius because we have something going along a circle. So that's why I started here. And then if this is true, or I can assume this to be true, work done by non-conserved forces equals 0, there's a good chance I'm going to use conservation of mechanical energy. I didn't think motion equations because we've got something that's going around in a circle and we don't have any angles to really find components and deal with stuff like that. So motion equations didn't jump out to me. Also, if you haven't figured out yet, this will not work on test day, but you can always look at the section that you're in. There's a good chance you're going to use whatever that is. So this is all the questions after 32 up until I think it's 55 are in the section for conservation mechanical energy. So there's a good chance you're going to do this. The other thing you can do, if you know what section you're in here of the problems, it starts here and then keep going. It goes to 45. So 32 to 44 are conservation mechanical energy. You can go back and look at that section in the book and look at sample problems and see what they did there, and then try to apply those ideas to this problem.